Okay, let's look at some examples for Module 9, talking about transformers. So this is a made-up example, but say you have one of these wall wart kind of things that you plug into the wall to charge some battery pack or something or other, maybe something like this. And so they most likely would have a transformer in them, probably have lots of other stuff too, but let's just kind of take something like this and go with it. So we'll say we have we'll call it we'll have an ideal transformer in the circuit, but this is more of a realistic transformer model here. So we have our ideal transformer here, but then we'll have this, we'll call it J800 ohms or so, to represent the magnetization of the core of the transformer. And we'll have just some resistance and some inductance to represent the coils. So this is more of a model of a more realistic transformer that would have the ideal transformer, which is lossless, and then we have the inductors and resistors, and some models will have another resistor in here too, to model the losses in the system or in the transformer itself. All right, and so we'll have the source here, some sort of VS. We'll have some sort of source current, which would be like coming from the power company when the thing is plugged in. And we'll have our normal kind of transformer set up for the ideal transformer. Let's see, I think we're going to go with like 110 to 9 on that. And we have some current I1, current I2, and we'll have our Z load out here. So in between here is the whole transformer, the realistic version of the transformer. We have our load on that side on the secondary, and we have our source on the primary. All right. We'll just give this current here a name. Let's just call it IX. And let's just call the voltage drop across all of this impedance V drop. Okay, just kind of treat this as one impedance with impedance of 1 plus J3 ohms. Okay, so let's see what we can do. So let's say we're given, we'll probably do this two different ways. We'll start with knowing stuff over here and going this way, and then maybe knowing stuff over here and going that way. And so let's just say that we have a load. And so when we specify voltages somewhere, you know, the active variables of a current, of a circuit are the voltage and the current, right? And power comes from that and so forth. Specify that somewhere, that we usually can work our way backwards. And so let's say we know V2, let's say it's at the nominal. If this was kind of a voltage ratio, lots of times transformers give their turns ratios as nominal voltage ratios. Sometimes it could just be 10 to 1 or what have you, but sometimes they give it as voltage ratio. So let's go ahead and say that V2 is 9 at an angle of 0 degrees. So let's pick V2 to be our reference voltage. And let's say that we're charging something, or that the load is drawing 20 watts and has a power factor of 0.7 lag. Let's just go 0.707, so then we get the 45 degrees. Okay, so first thing we want to know is, what is the power of the load? So what is S2? All right, and so we've got some pieces of S2 here, some information about S2 here. So what is this? It says watts. So that means it's the real power of the load. So the real power of the load is 20 watts. We've got the power factor. Power factor is, we have two different equations for it, maybe more, but these are two equations for it. The power factor is how much is the real power over the apparent power. So how much of the power is the ratio of the complex power magnitude to the real power, and it's also cosine of the angle, the power angle. So we can use this first part of it to get the magnitude of S, right? So the magnitude of S2 in this case, just multiply through and divide through by the power factor, is P over the power factor. And so we've got P is 20 watts, power factor is 0.707. So we got 20 divided by 0.707, 28.3. PA. And then we also want theta, so to get S as a complex number. So let's do, let's just do it over here. Theta equals take the inverse cosine, plus or minus inverse cosine of the power factor. So plus or minus, because when we take cosine of something, cosine of the positive angle and cosine of the negative angle are the same. We don't know which, so that's why we have to say lead or lag in power factor. So when we have lag, that means theta is positive, right? And so theta is going to be plus cosine inverse of 0.707, and we can do it, but that's a 45-degree angle, right? Square root of 2 over 2, cosine inverse 0.707, 45 degrees. All right, so S2 then is magnitude 28.3, angle 45 degrees, volt amperes. All righty. Next thing we want to find is I2. What is I2? Current over here, current in the load. Right? Messy stuff here. But so the current in the load, well, we can use the power information to get the current. And so we used to have PIV, P equals IV, but now we're complex, so we have S equals I conjugate V, or S is V I conjugate. We'll do everything 2, right? S over here is S2, I've called it, is V2 and I2. And so we can say I2 then must be S2 over V2 conjugated. Remember conjugate, when you take conjugate of something, you make all the angles negative and all the J's negative of what they were. Okay, so we've got S2 28.3 at an angle of, let's just go ahead and take the conjugate as we're doing it. So negative 45 degrees is S2 conjugate, and then we'll put V2 conjugate down here, which is, well, negative 0. Anyway, doesn't matter. So, but we got it. When you take the conjugate of a fraction, you take the conjugate of the of the top over the conjugate of the bottom, right? Okay, my computer's doing strange things here. Hopefully it's still recording the video. Okay, and so we can get I2 then. When we divide complex numbers, we divide magnitudes, so 28.3 over 9, and then we subtract angles, so negative 45 minus 0. And so 28.3 divided by 9, 3.14, at an angle of negative 45 degrees. Amps is I2. Okay, that's good. Let's go for part C. It says, what is Z of the load? All right. Well, Ohm's law, right? V equals IZ. So Z equals V over I. Right? In this case, we're talking about ZL. So ZL. At the picture, what is the voltage on ZL? It's V2, right? Minus on this side, plus on this side. So the load is in parallel with this side, this coil, the side of the transformer, and the current is I2. So it's just going to be V2 over I2. V2, 9 angle 0. I2, pi, for some reason, pi at an angle of negative 45 degrees. And so we got 9 divided by 3.14. 2.87 at an angle of, divide complex numbers, subtract their angle, so 0 minus a minus 45 is plus 45 ohms, ZL. All right. What else do we want to find? Working our way through, we got D, we want to know what is I1. You see that? Yes. Okay, so we were over on this side. We got pretty much everything figured out over here. So now we're going to come through the transformer, the ideal transformer, and start finding stuff over here. So we'll find I1 and V1 here soon. So I1 is what? Well, remember ideal transformer equation. Current goes opposite of the turns ratio. So the side with more turns will have less current and vice versa, right? And so we want I1. So I1 is N2 over N1 times I2. N2 is 9, N1 is 110, I2 is that pi number, 3.14, angle 45 degrees. All right. So again, the transformer turns ratio is just a real number, multiplies the magnitude, doesn't do anything to the angle. So I1's angle will be the same as I2's angle. So we're going to do 9 times 3.14 divided by 110. So I1 is 0.257, angle of 45 degrees, amps. Alrighty. E. What is V1? Same idea. We got the transformer equation because we're coming through, bringing the information through the turns ratio so we can keep on solving our circuit. So we have our other transformer equation. V1 over V2 is N1 over N2. So this is just the opposite. The more turns there are, the more voltage there is. You know, from Faraday's law, we has V is N dphi dt. So bigger N, bigger V. All right. And so V1 is N1 over N2, V2. And that is 110 over 9 times V2 was 9. And so since we made the load be at its nominal voltage or its rated voltage, then the V1 will be also. So this V1 is just going to be 110, angle 0 degrees. Good. All right. Next thing, continuing on through the circuit, we need to figure out what IX is. All right. So let's say Fix is what? I guess we need the circuit back here. So Ix is the current through this 800 ohm inductor, J800 ohm inductor, and its voltage, the voltage of the inductor is V1, right? So because the bottom is here at the negative of the coil, all right? So the inductor is in parallel with the high side of the transformer coil. All right. So we can just do Ohm's law because we got the voltage, we got the Z, so we can get I. All right. So Ix is going to be V1 divided by J800 ohms. All right, because V1 equals Ix times Iz, so J800. So gives us that. V1 was 110, angle 0. And this is 800 angle 90. We want to go do the in polar form, right? A J is something times J is something right up here, and so its angle is positive 90 degrees, right? So we get 110 over 800 at an angle of 0 minus 90 degrees. All right, so Ix is 110 divided by 800 0.138, and the angle is negative 90 degrees. Okay. G. Let's find what is the source current. Okay, keep on working our way back. So if we want the source current, Is, well, we know I1 and we know Ix. So we can do KCL here because Is comes in and it splits up into I1 and Ix, right? So KCL says in equals out, Is equals I1 plus Ix. Should be fairly simple, except for the complex math. But so Is is equal to I1 plus Ix. Right, so I1 0.257 angle 45 degrees plus Ix 0.138 angle negative 90 degrees. And we can convert this with Euler and so forth, but let's leave this one, let the calculator do this one, but let's change this. So negative 90 degrees, then if we do negative j, would be something down here, or negative 90 degrees would be down here, negative 90 degrees, and that's just a negative j. So 1 at an angle negative 90 is just negative j. So we could rewrite this. I'm going to put it in my calculator this way. Minus j 0.138. All right, because minus j is the same as 1 at an angle negative 90 degrees. Okay, so let's do this. So we've got 0.257. Got to get my angle symbol here. 45 degrees. Minus j 0.138. Okay, let's put that in polar form. So 0.187 at an angle of 13.5 degrees. IS. Just checking, looks like that's right. Okay, amps, of course. Okay, so we got IS. We'd like to get VS. How can we get VS? Well, we can look at KVL around the loop. So if we go, start here, negative VS plus V drop plus V1 equals 0. All right. So this, we'll call this GH. What is VS? So we said negative VS plus V drop plus V1 equals 0 from KVL. Just double check. Negative VS plus V drop plus V1 equals 0. All right, so VS is V drop plus V1. Old news on the back there. Okay, so VS then is, what is V drop? It's the voltage across this impedance, which is a combination of resistance and inductance. We can just use Ohm's law, V equals IZ, right? So V drop equals IS times this Z. So let's just write it here. V drop equals IS times 1 plus J3, Ohm's law, right? And so we put that in here, so we're going to have IS, I guess we'll just write it in here, 1 plus J3 plus V1, which was 110 angle 0. IS we also have somewhere, this is an S, not a 5. There it is, IS 0.187, angle of 13.5 degrees, times 1 plus J3, plus 110. 110 angle 0 is 110. Okay. So let's put that in the calculator. So we'll put the 110 first, plus, my calculator likes complex numbers in parentheses, so 0.187, get an angle, 13.5 times 1 plus J3 I think I got that put in there right. All right, and let's get it into polar. Oh. Something doesn't look right. So these currents are pretty big. So how did I get such a small number from that? sorry about that. I think, yes. The current I2 has a negative 45 on the angle, so I1 should have a negative 45 on the angle. So this should be a negative 45 on the angle. Let's plug that in again. Okay, 0.257 angle negative 45 minus J.138. Let's try that. And polar form. Okay, that looks better. 0.368. Everything's wrong. 0.368 at an angle of negative 60.4. Okay. And so that was IS. 0.368 angle negative 60.4. Try this again. Let's find it up here. Be lazy. Okay, so we got 110. And we're going to have the 1 plus J3 is the same, but the angle should be negative 60.4. And the magnitude 0.368. 0.368 negative 60, 1 plus J3 plus 110. And put it in polar form. All right, that looks more like it. V sub s 111.1. Okay, and the angle is very little, 0.1, 0.12. I don't know if it's worth keeping those sig figs, but anyway, 0.12 degrees. Okay, so there's Vs. And so we get some voltage drop across this guy. So right here is 110, but to get the transformer to be at 110, say its nominal value, the source has to be a bit higher, 111. Okay, so there's just roughly a 1 volt drop there, although it's complex math to figure out what the drop actually is. Okay, so that's H. What's next? Let's say I, we want to find the source power. So for I, what is the source power? Complex source power. So I sub S. S is VI conjugate, or sieve, S instead of piv, sieve, I conjugate V. But these are both the source current and source voltage. And so source current 0.368 angle negative 60.4 conjugate, and the source voltage was right there, 111.1 angle 0.1. Okay, and so multiply complex numbers, you multiply their magnitude, so it's 0.368 times 111.1, and angle wise this is going to become positive 60.4 because of the conjugate, and multiply numbers, you add their angles, so plus 0.1. And so 0.368 times 111.1, 40.8, 40.9, 40.9, and an angle of 60.5 degrees. Okay. VA. So that's S sub S. HIJ. So for J, it says, what is the efficiency? Efficiency is usually the Greek letter eta, or often is. And so efficiency, remember, we can do it with energy, but lots of times we do it with power. And so it's power out over power in. Okay, so in this case, it's going to be power 2 is the power out, and power of the source is the power in. So it'll give us the efficiency of our transformer. And so since our transformer, we're using a realistic model, it has some resistance in it. So we should have the power in be a little bit more than the power out, right? The ideal transformer it doesn't lose any power, but my realistic version, we should lose a little. All right, so what is P2? Well, remember at the very beginning, we were given P2 is 20 watts. How about PS? Well, PS, we can use, it's going to be the magnitude of S cosine theta sub S. So 40.9 cosine 60.5. Oh, what is this? Okay, maybe I should have kept some more sig figs. But anyway, 20.1. At least it's bigger. All right, 20.1 watts. And so the efficiency then, power out over power in, 20 over 20.1. We can take it, usually it's expressed as a percent, multiplied by 100%. So 20 divided by 20.1 times 100. 0.995 times 100, 99.5% efficiency. Okay, so this is just made up numbers, but that's how you would do it. Okay, so computer's acting weird again, but hopefully we're still recording. That's problem number 1. Let's look at problem number 2. Let's kind of look at it backwards a little bit. So let's say we've got the same, I guess I can redraw the circuit. Got the same circuit, our source, so this 1 plus J3, this element in our transformer model is representing the wires, the inductance and resistance of the wires, and we've got our J800 ohms for the core, magnetic core of the transformer, and then we've got our ideal transformer here, and then we've got our load. This is 110 to 9. So forth. All right, so this time, let's say we know VS. Let's say VS is actually going to be 110 angle 0 now. All right, so the source is at the nominal voltage level for the transformer or what have you. And let's say we do need to know what ZL is. So let's just go ahead and use our ZL we had before. I know we found it somewhere. ZL. There it is. So ZL is 2.87 at an angle 45 degrees. So let's just go with that. Okay, so let's say we know ZL, so that's just a passive element on this side. We don't know any of the active stuff over here. We don't know voltage and current over here. And we know the voltage over here now. All right, so how can we calculate or solve the circuit? Find the efficiency. What have we? So this is where we can use the equivalent impedance of that basically looking at the equivalent impedance through the transformer. So looking at the load, see what it looks like through the transformer. And so let's get some more paper here. Let's see it here. And so if we redraw and we think of finding it's kind of like a Thevenin equivalent looking in here, but there's no source in there, so it's just going to be a passive thing. It's kind of like finding the equivalent resistance of parallel series combinations, but now we got a transformer in there. And so we're going to have our stuff out here. This is just the same. But now past the transformer, or where the ideal transformer starts, we're just going to make all of that become Z1, well, let's call it Z1 equivalent. I'll call it something. So it's looking in to these terminals, we call this A and B, is the same. So we're looking and finding the Thevenin equivalent, looking through the transformer, and the transformer is going to be gone, but we'll still have I1 and V1 here because that's the voltage and current into those terminals, and we still got IX J800 ohms here, 1 plus J3 IS V drop. So this part of the circuit is all the same. Doesn't know that the other part is gone. We're just going to find the equivalent impedance for that. And so remember, we have the transformer equation. Ideal transformer equation says Z1 over Z2 is N1 over N2 squared. If you want to prove that, it's not hard to prove, just using the other two transformer equations. I'll give you some extra credit points if you want to prove this for me. Okay, but we're going to just use it. So Z1, so that's these are the Z's looking into the transformer, one side or the other, right? So Z1 is V1 over I1 looking in here, and that's what we want Z1 equivalent to be. So Z1 is Z1 equivalent, or Z1 equivalent is Z1, is Z1. Solving this for Z1, we get Z2 times N1 over N2 squared. And so Z1 equivalent for this case is Z2 is Z load, right? V2 over V1, Z load. And so Z load is 2.87 angle 45 degrees times N1, 110 over N2, 9 squared, right? Again, this is just a real number. It's just going to change the magnitude. The angle is still going to be 45 degrees. So we're going to have 110. Let's put this in parentheses. 110 divided by 9 squared times 2.87. All right, so the magnitude is 429. Angle still 45 degrees. So this is Z1 equivalent. That's what it looks like. What's the transformer looks like from this circuit, all right? Looking in from there. So it's our equivalent, remember, Thevenin equivalent, looking into those terminals. There's no source in the original, so there's no source in this one. Okay, so we got Z1 equivalent. Now it's just kind of a basic circuit to solve, right? We know the voltage here. We have 1 plus J3 in series, and then we have the J800. This doesn't really have a name. Call it JX sub M sometimes. JX sub M in parallel with this Z1 equivalent, right? And so if we want to find the total, we say Z total. Whoa, getting off the page here. Z total for the whole circuit. We're going to have 1 plus J3. All right, that's the series part. In series with, so when we say in series with, we add, and then these two in parallel. J800 in parallel with Z1 equivalent. All right, hopefully you see that. The bottoms are touching, tops are touching, so those two are in parallel. And then if you combine that into one thing, that thing is in series with the 1 plus J3. Okay, so we got 1 plus J3. So why are we going to do this? We can use this then to find the source current, because we're going to boil it down to one impedance, Z total, but the source is still here. So we can just do Ohm's law then to calculate IS is going to be VS over Z total. All right, so that's why we would find this total impedance in the first place, just to solve the circuit. We could do mesh currents if we wanted to. We could do mesh currents instead. Should we do that instead? We'll just go ahead and do this since I'm started on this. So 1 plus J3, so we're going to have J800 times 429 at angle 45 degrees divided by J800 plus 429 angle 45 degrees. All right. Thank you, God, for good calculators. Let's do this. So we got 1 plus J3 plus, so on the top we can multiply these two. Remember, J is a 90-degree angle, and so we can just have 90 plus 45. So this top is going to be 800 times 429 at an angle of 90 plus 45, so 135. Okay, that's the top of the fraction. And then we want to divide that by this, which I don't really see a way to simplify, but let's go ahead and put in parentheses 429 at an angle of 45 plus 800 J. Oh, what's the matter? Oh, I didn't put parentheses around what I'm supposed to put parentheses around. Put another parenthesis there. Okay, parenthesis around the polar form there. This on the top and the 1 plus J3 there. Okay. Let's go ahead and get that in polar form. Oh, come on. Just show me a number. There we go. So Z total is 303 at an angle of 60.5 degrees ohms. Alrighty. Good number. Let's put a box around. I didn't really ask. We're not really specifying what we're looking for here, but we're just kind of going through the circuit. So now we got Z total, so we can get IS. So IS, and we were given VS, so IS is VS over Z total. VS is, we said, 110 angle 0, and Z total 303 angle 60.5 ohms. So that's going to be 110 over 303, angle negative 60.5. 110 divided by 303. Oh, come on. So IS this time is 0.363, angle of negative 60.5 degrees. And so we expect this to be pretty close to what we had before, but the voltage is just a little different. Remember, the source voltage was 111 when we started with the information over on the other side, but now it's 110, and we use the same Z. So let's just kind of take a peek. What was IS before? Yeah, IS was 0.368, angle negative 60.4. So pretty close. So I think we're calculator's behaving itself here. I hope it's still recording. Not sure what's going on with my computer. Okay, we'll keep going. So, but I can't see the screen. Come on, computer. Let's do this. Okay. Okay, so we got the source current. Trying to solve the circuit here. Now we've got to work our way into the circuit. Do we want to do all this? I guess we will. Let's keep on moving. I have some more paper here. So, as we want to calculate V1, calculate the voltage here. Because we want to get the current and so forth, we'll need to know the voltage to get the current. We've got IS, so we can get the drop across here. And so let's go ahead and figure out what is V1. There we go, can we see that? So V1 is what? Remember from the KVL, we had said negative Vs plus V drop plus V1 equals 0. So rearranging, this says that V1 must be equal to Vs minus V drop. Right? And V drop is just I times the Z of that series resistance. So it's just going to be IS times 1 plus J3. Okay. Pages here. And so V1 is Vs, 110 angle 0, minus Is, 0.363 angle negative 60.5, times 1 plus J3. Okay. 110 minus 0.363 at an angle of negative 60.5. Multiply that times 1 plus J3. Okay, and then convert that to polar. So 108.9 angle of very little, 0.12 again. All right, so last time V1 was 110, and then the source voltage was 111 magnitude-wise. Now this one is 109, and the source voltage is 110. So again, about roughly in magnitude-wise a 1 volt drop, but again, complex, so you can't say it's exactly that. You can't just subtract it magnitude-wise. All right, so we got V1, so we got V1, so we can get Ix, and then we can use Is and Ix to get I1. Let's get Ix first. Ix is what? It's going to be V1 over J800, because V1 is the voltage here. Do we even need to do that? Let's just not do that. Actually, we don't need to find Ix because we want to find stuff about the load, which is over here in the inside of this Z1 equivalent. So let's just go ahead and get I1. Right? We can get I1 because we can do Viz over here. V1 equals I1 times Z1 equivalent. So we could do that, but we don't care. All right, so I1 equals V1 over Z1 equivalent. V1 is 108.9 angle of negative 0.12. Z equivalent 1, Z1 equivalent 429 angle of 45 degrees. Okay. So I1 is 108.9 over 429 angle of negative 0.12 minus 45. 108.9 divided by 0.254 at an angle of negative 45.1 degrees. Amps. I1. All right, we're getting somewhere, I think. And so now let's put our circuit back together. Where is the whole circuit? Lost my circuit. There it is. Okay, so remember we had equivalence, Z equivalent 1 represented all this, but now let's get it back so we can actually see what's going in on the load. So we've got I1 and V1. Do we have I1? We have V. We just got I1. Yes, we got I1 and V1. Yes. All right, so we can get I2 and V2 because of the ideal transformer relations. And then we can calculate power and efficiency and all that. Yay, we're getting there. Okay, so let's say we want I2 and V2. So these, we just use the ideal transformer relationships. So I2 over I1 is N1 over N2, multiply through by the I1, so we get this, and so we've got N1 was 110, N2 was 9, I1 0.254, angle negative 45.1 degrees, 110 times 0.254 divided by 9, 3.10 this time at angle negative 45.1 amps is I2. Remember, it was 3.14 last time, so again, it's close, so we'll leave it. V2 over V1 is N2 over N1. Remember, voltage 2 on top means N2 is on top, but let's multiply through by V1, and so then we have 9 over 110 is times V1, which is 108.9, angle negative 0.12. All right, so current goes up, voltage goes down, right? And so the power stays the same going through the transformer. So V2 is 9 times 108.9 divided by 110, 8.91 at an angle of negative 0.12 degrees is V2. Good. Okay. And so we've kind of got everything solved. And so let's find the efficiency. It's going to be power 2 over power in, power S, power out over power in. So we need to get those. Power 2 is the real part of S2. All right. So P2 is magnitude of S2 cosine theta 2. Magnitude of S sub S, cosine theta sub S. Oh, do we have this stuff? Let's see. I guess we don't have any of this stuff. Okay, so well, we can get it. So S is VI conjugate. How do we want to do this? And so do we need to go ahead and just, we can just go ahead and calculate S2 and S sub S. I guess that would be the neatest way. So S2, V2, I2 conjugate, V2 8.91, angle of negative 0.12, I2 310, angle of negative 45.1 degrees, conjugate. So we get 8.91 times 3.10 at an angle of negative 0.12. So it's the conjugate and the negative 45. Conjugate means make the negative of the negative, so it's going to be plus 45 degrees. So S2 is 8.91 times 3.10, 27.6 at an angle of 44.9 degrees. VA, we need more paper. Okay. Let's convert that to rectangular. So S2, I'll just write it again, 27.6, angle of 44.9 degrees. If we want to write it according to Euler, 27.6 cosine 44.9 plus J 27.6 sine 44.9. 27.6. Of course, our calculator could do it for us too. Polar to rectangular conversion. Oops, I didn't mean it. Sorry. Cosine 19.6 plus J 19 point, oh, well, it's pretty close. 19.5, pretty close to 45, so it's pretty close to the same, right? P and Q. So actually, we were just looking for P2. So P2 is 19.6 watts. Remember, last time it was 20 watts. All right. S2, I'm sorry, S sub S is VS IS conjugate. If we just want, well, let's just go ahead and do it. If we just want the real part, we could just do magnitude of V, magnitude of I, but we've got to get the angle anyway, so we might as well just go ahead and do it. So VS was 110 angle 0, IS is here somewhere. Is here somewhere. IS 0.363 angle negative 60.5. 363 angle negative 60.5. Alrighty, so VS is 110 times 0.363 angle of a negative 60.5, so positive 60.5 degrees. VA. So P sub S, well, I guess we can calculate it. 110 times 0.363, 39.9 angle of 60.5 degrees. VA. So PS is going to be magnitude of S cosine theta. So 39.9 cosine of 60.5. So PS is 19.6. Oh no. Oh no. 19.65. And let's redo this one. 27.6. We're kind of cheating on the sig figs here. 27.6 times cosine of 44.9. 19.55. It's such a small difference. I should have kept 4 sig figs all the way through to be fair, but we can get a number here. So efficiency is power out over power in. Power out is P2 19.55 and power in is PS 19.65. Take it times 100% to get it as a percentage. 19.55 divided by 19.65. 99.5%. Still very close to being in the rounding error, but there we go. Okay, so hopefully that gives you an idea of how to deal with transformers, ideal transformer, turns ratio, impedance, equivalent impedance, all of that fun stuff. All right, I think we'll stop there.